Introduction to LTE. As you know, LTE stands for long-term evolution. Many of you have LTE. We are using LTE. It started out in 2010. Actually, the 2000, I think around 2010 or 11 we started seeing it here. We talk about what is 4G first, and then we get into LTE, and then what modulations, etc. it uses, how does it do the resource allocation, what does the network look like, what do the frames look like, and so on and so forth. So we go a little bit more detail in this stuff. What is 4G? There is a very well defined official definition of 4G. And this is the job of the ITU, ITU to define this. And back in 2003 to 6 time frame, they started discussing what should we do in the long term. I mean, not the long term. They started discussing what should we do in the future. And in 2008, they published a document, and actually we were aware of this in 2006, that said that this is what we need in the 4th generation. First of all, it should be IP based. So by this time, it was very clear there is no competition. Because if you go back 5 years before, there was competition, there was OSI and this and that, and you go back more 5 years, there was DECnet and SNA. But by this time, IP is the king, right? So it has to be IP based. Second thing, we should get at least 1 gigabit per second for fixed services using 100 megahertz. Or 100 megabits per second if you are moving very high speed, and the speed here is 500 kilometers per hour, which is really, I don't think you can drive that speed, but that's the goal. I don't know what they were thinking of, but anyway, so 100 megabit and 1 gigabit, yeah, go ahead.
Well, does that mean you could use 4G on a plane?
Well, planes actually go much faster than that. That's why I said I don't know what they were thinking of, because planes, when they land, towards landing time, very just, like a few minutes before landing, they're flying at 1,000 knots, which is like 1,200 kilometers, or 1,600 kilometers per hour. So I don't know how fast they fly in the sky, right? So it's not that, for sure. Yeah, this could be high-speed train. That's valid. High-speed trains do run at that speed. So, 500 kilometers per hour. Seamless connectivity and global roaming with smooth handovers. And this was also clear that we really don't want to have a patchwork. So we want to have global roaming. Anybody can take the phone anywhere and it should work, right? High quality multimedia. But more importantly, there were some very specifically defined numbers. And I'm really surprised that they could come up with these numbers to the second decimal digit that they should meet. Okay. Downlink spectral efficiency, which is BPS per hertz, should be 2.2 for the cell wide, peak should be 15, and the edge should be 0.06. So why are the 3 numbers? First of all, we are talking about the downlink from the base station, right? Peak, where is the peak? The peak is near the base station. Near the base station, power signal is very high powered. There is very little noise from other places, and you should be able to get 15 bits per hertz. What happens at the edge? At the edge, you are at the mercy of your neighbor, right? You have a lot of interference, and so you cannot really get anywhere close to 15. You go down to 0.06 bits per hertz. Okay, so the overall cell should be 2.2. You are varying from this extreme to that extreme, but on the average, we should be able to get 2.2. Now, uplink spectral efficiency is always lower. Why? Because the power is very little. The mobile is transmitter, so it is not going to be transmitting as much power as the base station can. And second thing, there is a lot more interference. From when the base station transmits, everybody listens. a lot of quietness, right? You get better results. When people are talking, just the opposite. Everybody is talking, and so there's a lot more interference. And so, if you get 6.75, that would be 4G. 0.03 in the edge and 1.4 overall. Data rate. So with this kind of efficiency, and given that you could get up to 100 megahertz, you should be able to get, well, actually these numbers are for 40 megahertz, that is up to. And so this is 40 megahertz, you should be able to get 600 megabits peak and 2.4 at the edge and 88 at the. So actually, it turns out that these numbers are very easy to calculate. You multiply 15 by 40. If I give you the efficiency and give you the bandwidth, you should be able to get the data rate. Right? If I ask you to design a technology which gives you 15 bits, 15 BPS per hertz, and I give you 40 megahertz, how much will you get? 600. Similarly, this number is similarly 40 times that and 40 times that. Uplink number is exactly the same. So these two lines could be even be removed and asked me as a question, but basically that's what it is. Everybody understand the bottom two lines? All right. So there were competitions, there were proposals, and both LTE and WiMAX knew upfront before the requirements were published in 2008, they were known in 2006 that they do not meet the requirements for 4G. So they started working on their next generation. LTE Advanced and WiMAX Release 2, which were ready in 2010, were taken to ITU, and ITU verified that they meet the requirement. So we have two 4G technologies, LTE Advanced and WiMAX Release 2. WiMAX Release 2 is also known as 802.16m-2011M, letter M. WiMAX itself is E. If you talk about WiMAX, you just don't put the Release 2, then it is 802.16E. And this is M. LTE Advanced, obviously the word advanced is there. So LTE they are not 4G, but they are near 4G. Now it's very difficult to put a number there. They're like 3.9G. So for a marketeer, that's 4G, right? And so they are being sold as 4G, but they're not. However, having said that, I said last time again, and I'm going to repeat it, I don't think now you can sell these other technologies as 4G because they're superior. So they will probably just have to skip a generation and call them 5G. But that has not happened yet. Okay? But we are going to talk about 3.9G in this lecture, 4G, real 4G in the next lectures. LTE. Again, I can talk about both WiMAX and LTE. However, given the time that we have, I'm not able to talk about WiMAX because LTE is more important and more prevalent. And I have my lectures on WiMAX. I've spent 4 years of my life on WiMAX. I have my papers on WiMAX. However, I will keep that until we really need it if we have time. So they're going to do LTE. Long-term evolution. So this came out 2009, release 8. Now, I must explain releases. So 3GPP, as you know, is the third generation partnership project. That's a group that developed all the standards for 3G. And they have every year they have a release, new release. And a new release comes up with the new features. All right. And so release 8 was released in 2009, and it has all these things what we call LTE today. And then there is release 9, there is release 10 and 11 and so on and so forth. So release 8 in their term is LTE. So initially developed as 3.9, pre-4G, now it is sold as 4G. Many different bands. So now this has this actually basically meets all, I mean, this is basically moving along the direction where the 4G people wanted to go, is that it should basically be able to work on any band. And so it works on these bands. And the problem with the bands is whatever is available, whenever it is available, people use it because spectrum is hard to find. So 700, 1500, 1700, 2100, 26 megahertz, 100 megahertz implementations are there. Flexible bandwidth. Whatever bandwidth you can find in those bands, it will work on. 1.4 megahertz, 3.3 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, 20 megahertz. You know, if you can afford that much, because these things cost 50 cents a megahertz per person. And there are 4 billion people. So they're really expensive. All right. So these bandwidth. And then if you can find paired spectrum, paired means up and down, FDD, it will use it, or TDD. If you don't find paired spectrum, it can use TDD in one spectrum. So both paired and unpaired. So this is basically very flexible in terms of spectrum. By the way, all of this applies to WiMAX as well. I mean, if I give a lecture on WiMAX, this will look like a repeat. Actually, this is a repeat of WiMAX because WiMAX was there first, and then LTE came along and they said, okay, all of this, let's call it LTE. So basically, all of this applies to WiMAX as well. 4x4 MIMO, multi-user collaborative MIMO. So they have some new MIMO techniques that we'll talk about. Beam farming in the downlink. What does beam farming mean? Anybody knows?
It determines the best configuration of the
Configuration of what?
antenna.
Yeah.
Antenna.
Configuration of antenna. Yeah, okay.
I would
Good.
say it's the focus of
Directionality.
directionality.
Okay. Good. So beam farming is basically directionality, and it's not static directionality, is that it is dynamic directionality. Focus like this, talk to you, focus like that, talk to you, focus like that, talk to you. So basically, dynamic directionality. Data rate, it can get you 326 megabits down, 86 megabits up using 4x4 MIMO and 20 megahertz. Alright, we're almost there to 15 bits bps per hertz. Modulation, it can use QPSK, 16 QAM, 64 QAM, etc., etc. Downlink is OFDMA, uplink is not. Okay? So the uplink is single carrier frequency division multiple access, which is SC-FDMA. Okay, we'll talk about that, what it is. It does hybrid ARQ transmission, short frame sizes of 10 millisecond and 1 millisecond. So basically one of the requirements of 4G and voice and for carriers, everything else is that we should be able to get access very fast. We should be able to turn around very fast. So the frame sizes are very small. Every 10 millisecond or 1 millisecond there is an opportunity to transmit. So that means faster feedback and better efficiency at high speed. Okay? And here speed means two things actually. I think it really means high speed means this, 326 megabits, very high speed, as opposed to mobility, which is 500 kilometers per hour. Faster feedback and better efficiency at these speeds. Persistent scheduling to reduce control channel overhead for low bitrate voice transmission. So really you don't want to be asking for bandwidth and going back and getting the bandwidth going back, and so you can just give it once and say, okay, all right, come back every day and just transmit 5 bits. And so that kind of called persistent scheduling. IP-based flat network architecture. All right, having said this, I'm going to keep saying this many, many times. All of this is also true for WiMAX, except for that SC-FDMA. WiMAX is OFDMA in both directions. And if I find myself saying all of this, then I might as well have a lecture on WiMAX first and then do this. But right now this is LTE. And just for the sake of completeness of this lecture, I have put one OFDM slide that you have seen and you basically know, but just to be sure, OFDM simply means that we take a big channel, wide channel like 20 megahertz, and divide that into smaller channels of whatever number you want, and then modulate each carrier. So that way each carrier is very small, and you do all this in parallel transmissions on multiple carriers. That is OFDMA. And the advantage of that is that because each channel is very small, the symbols are so big. The bits are so big. Because if each channel is 300 megabits, then each bit is 1/300 microsecond. If each channel is 1 megabit, each bit is 1/1. So it's much bigger. And the advantage of big symbols is that when they collide, they don't lose much. So inter-symbol interference. Inter-symbol interference is reduced for long path variation. So if you are taking this path and you're taking this path, they will come and at different time and they will collide. They will eat each other up. But because they are so big, they still survive. Little bits will get lost. So OFDM is now the technology that we use. And the interesting thing is that even though it looks like they're going to have 1024 carriers or 2048 carriers, you don't need that circuitry because there is no hardware required. There is no real radio hardware. There is all mathematics. It's all done in mathematics. It is all done in a computer where all you're doing is not really using any radio signals. You're using bits and numbers. Numbers are we do FFT and IFFT. Fast Fourier transforms and inverse fast Fourier transforms. So this is all done in numbers and not in voltages. Okay, and I will show you the circuitry in a minute. So that's why basically at the end you really don't need that much of hardware. You just need, of course you need CPUs and things like that. If you do 246, you need a real good CPU there, but that is doable. The advantage is large symbol sizes. That means you can take up the multipath, and because you can take up the multipath, you can do MIMO. See, the reason the MIMO works is multiple input, multiple output, is that you send signals from multiple antennas. If you didn't take up the multipath, they will all get killed, right? Because we can take up the multipath, we can separate them out, and we can get much better data rate. So MIMO works much better with OFDM. Low computational complexity, easily implemented with FFT and IFFT, graceful performance degradation under excessive delay. So basically, when you design these systems, you have to decide how much path delay there is, maximum difference. So the shortest path is this, the reflected path is this, the difference is so many microseconds. We have to somehow make our symbol bigger than that, but what if you're wrong? So suppose you design for 0.5 microsecond and the delay is now 0.6 microsecond, would you get killed? The answer is no, it slowly comes down. Alright, so this is ideal for adaptive modulation and coding. So basically, you can change your coding, etc. easily. Frequency diversity. And then the data is spread across many subcarriers. Right? So robust against burst error. So if anything happens here, we don't lose the whole thing. Right? Robust against narrowband interference, which is actually somewhat similar. Burst error is in time, narrowband is in frequency. Right? When we say burst errors, we mean in time. 100 bits got killed together. When we say narrowband interference, we mean the frequency band. And actually the list continues. The numbering system should continue. So this was 5. The next should be 6. the allows pilot subcarriers for channel estimation. So that's another thing is that you can put these pilots, the blue color things, where you don't send data, you just send something so you can figure out what is the noise in this area. You know, what is this channel like this, right? Efficient multiple access and resource allocation. And then you can do resource allocation very easily. You can give somebody 2 carriers, somebody 15 carriers, somebody 13 carriers. Actually, you don't do those numbers, by the way. I will show you in a number, because if you start doing 2, 3, 15, it will become a very complex problem. You really take a bigger number like 12 and give them multiple of 12. You get 1 time 12, you get 3 times 12, you get 15 times 12. That's how you can allocate 2024 or 2048 carriers. Otherwise, if you do 1, 2, 3, it will be 2000 combinations. All right, so efficient multi-access. Efficient broadcast. And multiple base system can synchronize to combine the transmitted signal, enabling higher broadcast data rate. So obviously there are certain things which are broadcast and certain things which are unicast. If you want to do broadcast, then 2 towers can broadcast exactly at the same time, and you get twice as much signal. Okay? You couldn't do that for unicast because they will be saying something different, but here they are saying exactly the same thing. Disadvantage. Having done all these advantages, there is one disadvantage, and which is called high pepper. Pepper is peak to average ratio, not N. Peak to average ratio, not ratio. So peak to average ratio, and that increases the cost of the amplifier. So I will talk about that. I have a full slide on that. So anyway, we understand the advantages of OFDM. And then there is OFDMA, and one has to distinguish between the two, by the way. I have used it so many times, but I don't know whether you guys distinguish between OFDM and OFDMA. OFDM is, M is for modulation. In OFDMA, M is for multiple access. So this is an access method which actually builds upon OFDM. Right? You couldn't have OFDMA with CDMA. I mean, that would be, you could have that, by the way. Every time I say something, then I say, oh, there is an exception. So yes, it is possible, but generally you do OFDMA with OFDM. Right? So this is orthogonal frequency multiple access, and all this means is that you don't give all the carriers. In OFDM, just like they do OFDM in 802.11n, they don't do OFDMA. They do OFDM. There they give all the carriers to whichever station is transmitting. They get all 2048 carriers, period. So all they do is time division multiplexing, where for this time user 1 gets it, user 2 gets it this time, user 3 gets it this time. So this is TDMA using OFDM. Right? But if you really want to do OFDMA using OFDM, then for this time and this frequency user 6 gets it, for this time and this frequency user 7 gets it, and so on and so forth. You define both the frequency and the time bounds for the users. This is a 2-dimensional scheduling, this is 1-dimensional scheduling. Now why the CDMA is gone? CDMA is gone because it is not frequency selective. Means if you look at this picture, if something happened in this area, and by the way, CDMA is single carrier, right? The whole band is one carrier. So what will happen is if you miss this area, the whole carrier is gone. And so it is not frequency selective. Symbol period is short because now it is so big, symbols are so small. Equalization, now you have to equalize it. See what happens is when you transmit from here to there, you have to make sure that every frequency gets the same amplification, otherwise your symbol will look like this. So you have to have same power level, same amplification level, etc., for all the whole frequency band. And if the band is so big, you can't handle it. That's why 5 megahertz was the maximum limit, and that's why WCDMA, which is called wide band CDMA, uses 5 megahertz. They can't use any more. Okay. Here, 20 megahertz is not the limit, 100 megahertz is not the limit, 200 megahertz is not the limit. You give me the bandwidth, I will just find that many carriers. Resistance to multipath, of course, single carrier, and the cyclic prefix will fix it. MIMO is difficult because of the multipath. Here it is easy. Frequency distortion is averaged. So if there is a problem, different frequencies, different things, this will all be averaged out. Here it will show up as inter-carrier interference. Now here is the thing now, if you're thinking that the carrier is here and somebody put the carrier over there, of course there is a confusion. So that will show up as inter-carrier interference. Using multiplexing. So here the way you do multiple access is by giving different codes to different users. Right? Direct sequence spectrum. Here you do it by frequency and time. Giving different frequency and different time to different users. So now you should know CDMA, OFDMA much better and understand why CDMA is going and OFDMA is coming. Now a little bit of electronic circuitry, just to understand how this all happens. So you will notice that there is a circuitry here, but really the real signal is mostly here. Actually, the real signal is not even shown here, I'm sorry. Okay, so let me show you how it happens. These are all bits here. So basically, whatever bits you have, you add FEC to that. FEC is the forward error correction bits. Then you do QAM modulation. Now modulation means, you don't mean that you find a voltage here. You basically calculate what the phase would be, what the amplitude would be, right, of this thing. And so you will get many bits here, many basically symbols here, let me put it this way. They are all right now in computer memory. Okay? You do serial to parallel conversion. So now they are coming symbol 1, symbol 2, symbol 3, symbol 4. You put them symbol 1 on the first line, symbol 2 on the second line, symbol 3 on the third line, fourth line. So you just put them in memory in parallel. That this will go on some carrier, this will go on some carrier. So the numbers have been rearranged in parallel instead of serial. So now you have total of 2048 carriers or 10,048, 24 carriers. Whatever number of carriers you have, they are right here. Those are the memory locations. Make sense so far? Now you do sub-carrier mapping. Now it doesn't mean that this has to go on carrier number 1. What they do is they randomize it so that this goes here, that one goes there, that one goes there. So every user is everywhere. Okay, so this is another technique, is that basically we don't concentrate one user in one place. We want to make sure that they are not totally killed by one bullet. Right? So we put them in different places. So that is, all this is doing is, sub-carrier mapper is doing is, random, there is some formula here which says, okay, this is the formula by which these carriers will go here. And not only that, they have a random formula, so that that formula changes every few seconds, every few milliseconds. So the next time the user 1 is here, third time he is here, fourth time he is there, and everywhere. Anyway, so now this is all basically so far memories, right? Now we do IFFT. So we put a computer to it, CPU to it, and say, okay, I like calculate inverse fast Fourier transform of these numbers. Now we have the numbers. Now we make parallel to serial. So now we become one line. And then we put a CT. CT is the cyclic prefix. So we copy the first part, last part of the bits, put it in the front. And from here, then we put some circuitry. It goes on the air, comes back at the receiver. At the receiver, same thing happens. There is an antenna, there is a circuitry, and all it does is removes this CT, and somehow basically there is a D to A converter here, and there is an A to D converter here, so that analog becomes numbers. And then now this is all memory. What happens is we start first remove the CT, we do serial to parallel, then we do that inverse and the IFFT. This is IFFT, so this is FFT. Then we do demapping, and we do the equalization just to make sure that everything is same level. and then parallel serial, and then we basically select out. So the thing, they have 2048 carriers here, but the user only needs 120 carriers or whatever number it needs. It takes those and continues from there. So this is how OFDMA is implemented. Where is peak to average of paper? Basically, since each carrier is modulated according to a specific channel condition, there is a high variation of power levels. So some carrier, if there were real carriers there, because there are no real carriers in this system, by the way, if there is a carrier, it will have this value amplitude, this carrier will have this little amplitude, this carrier will have that amplitude, and so you will see a lot of amplitude variation all over. And therefore, the peak to average ratio is very high. And that means that you have to cover a very large range, and the amplifiers are the most expensive part of a wireless system. There is one component which overshadows the cost of everything else. It's the amplifier. Here are two components, amplifier and D to A converters, or A to D converters. So amplifier, generally, they are linear only up to a certain point. After that, they are not linear. So you have to make sure that your peak fits in there. And if your average is very high, then peak to average ratio is very high. Your average will be very small, and you will have really not good. Because you don't want a small signal, right? So peak to average ratio, and therefore you really want to keep this peak to average ratio as high as you can, so that really you are operating in some good zone without exceeding the peak. And so therefore we need to do something about it. And so for that they invented SC-FDMA, single carrier frequency division multiple access, which is in some sense is FDMA. Basically, but in some sense it is OFDMA too. In a minute I'm going to explain that. But basically, single carrier means user is given a small part of the band. User 1 is this much, user 2 is this much, user 3 is this much. This is a contiguous part of the channel. All right, and this way basically you have avoided this division. So you are going back to single carrier rather than multiple carriers using single carrier modulation, and then we add a cyclic prefix at the end, which is new. Basically, we didn't used to have cyclic prefix before in FDMA, but now we put cyclic prefix at the end. So single carrier means not much variation in the amplitude. Pepper is low, and better for uplink, because slight missynchronization among the user does not affect the decoding significantly. Now, so the thing is, in the uplink, as I said, the user 1, 2, 3, 4 all talking at the same time, and if they're slightly off, they don't kill the whole thing. And better for uplink. Okay, second thing is, with OFDMA, each user subcarriers are spread all over the band and may affect all other users, whereas here they're not spread all over the band, they're just narrow. So this is better. And I think I will stop right there, because we do need to do that exam thing. So we'll continue from here next time. Any questions about this?